radioactive, and it disappears within just a few days. If you look in the rocks on the surface of the Earth, which are hundreds of millions or billions of years old, if there was any technetium in there, it long ago decayed and disappeared. So there was a hole in the periodic table. But today, we can take element 42 molybdenum and bombard it with neutrons, and we can make element 43 technetium. So much so that some of you may have ingested or had injected into you technetium. It's commonly used in medical imaging today. If you ever had a radioactive tracer test, about 80% of all radioactive tracer tests today are done with technetium. So we use it in medical testing today, but for a long time, there was a hole here on the periodic table. So there are no holes left today, except you might argue, well, what about these big elements that scientists always seem to be coming up with new elements all the way up to unoctium up here on the periodic table? The thing about these giant elements down here is that we make them by smashing together smaller elements. And when we smash them together for a tiny fraction of a second, they come together and they form one of these larger, more massive elements. But all of these elements are so unstable that the vast majority of them decay in less than a second. So even if you make one of these atoms in one of these atom smashers, it's gone in less than a second. It disappears because it's so unstable, it decays into smaller atoms again. Even the most stable of these elements are not stable for much more than a second in time. So you can't really build a spaceship out of unoctium or any of these heavy elements because they decay in a second. And so I would argue that you can't make anything in the universe other than with this. So remarkably, our periodic table has on it everything that there is in the universe that gets made. The protons, neutrons, and electrons. It's on our periodic table. If you in the lab and explain all those things in astronomy that I'd love to know about that you haven't figured out yet, I can guarantee that there's a lot of protons, neutrons, and electrons. It's on our periodic table. So that raises the question, where do those protons, neutrons, and electrons come from in the first place? The stuff, the atoms that were made of, are made of those fundamental building blocks. Where did they arise? And the answer is they came directly from the Big Bang. The next time you're getting up in the morning, the young students won't understand this, but those of us that are my age will understand this, and you swing out of bed and you're sitting there and you're feeling kind of old and creaky that day. Regardless of how old you are, remember that the protons, the neutrons, and the electrons that make up your atoms are a lot older than you are. In fact, they date all the way back to the Big Bang, and they are, in fact, 13.7 billion years old. So that number, the age of the universe, was determined about 10 years ago by a NASA satellite called the Wilkinson Microwave Anisotropy Probe. We'll see a picture from it here in a minute. And it's one of the hardest fought numbers in astronomy. We fought for 100 years to figure out the accurate age of the universe, and now we know it. It's 13.7 billion years old. And the protons, the neutrons, and the electrons in your body were made in the Big Bang. Now, the Big Bang isn't just a hypothetical idea that astronomers have come up with. The Big Bang can be tested in laboratories today. And in fact, it was a simulation of a collision at the Giant Particle Accelerator in CERN in Switzerland. On the border of France and Switzerland, they take protons, and they smash protons together at high speed, because when those two protons meet head-on, the pressures and the temperatures and the densities in that collision are the same as they were a tiny fraction of a second after the Big Bang. Here on Earth, we can recreate the conditions of the Big Bang when we collide atoms like this in our atom smashers. And in fact, that's a large reason why we do it, is to make these kinds of conditions that we don't normally experience around us. So understand the Big Bang fairly well. You know that during the Big Bang, the universe was really hot. It was so hot that the universe was filled with light, and that light consisted of high-energy photons, a kind of light called gamma rays. And every now and then, these two gamma rays would collide with one another, and when they collided with one another, they would make a piece of matter and a piece of antimatter. And the only difference between matter and antimatter is the charge. So this, for example, is a proton with a positive charge, and this is an antiproton with a negative charge. And so when these photons would collide, they would make two pieces of matter. And the only thing that was required for these two photons to make that matter was that they have enough energy. Einstein's famous equation, E equals mc squared, tells us how much energy it takes to make a certain amount of matter. If you know the mass of the proton and the mass of the antiproton, you can figure out how much energy it took to make them. And it turns out the only form of light that has enough energy to make these things are highly energetic gamma rays. Now, fortunately for you and me, gamma rays are pretty rare these days. Unless you work in one of the nuclear industries or work here at JLab, you probably don't encounter gamma rays very often. But when the universe was filled with gamma rays, this was going on all the time. In the first few seconds of the universe, matter and antimatter were popping into existence as these photons would collide. The problem is matter and antimatter have opposite charges. And remember that opposite charges attract one another. The positive proton and the antiproton are attracted and they annihilate in a burst of energy, just like in Star Trek. When matter and antimatter come together, they annihilate and you get back those two photons of light. If this was the only way to make matter in the universe, then every time we made a piece of matter, we'd make a piece of corresponding antimatter. But for reasons that physicists don't understand right now, every now and then, in the early universe, the universe made a piece of matter, but it did not make the corresponding piece of antimatter. Or it made the antimatter, and the antimatter was so unstable that it decayed away, and all we're left with is the matter. But this is the matter, the protons that you and I are made of. They were made by light in the early universe, and those protons are the ones that remain because their partners either weren't created or decayed away long ago. The physicist, or the scientist who answers the question about why the antimatter wasn't made sometimes or decayed away, without a doubt will win the Nobel Prize in Physics. So my generation has been working really hard on figuring out this problem. We haven't gotten it yet, so maybe one of the students in here will finally be the person who figures out why it is that antimatter wasn't made and only matter was left over. Because today in our universe, there's essentially no antimatter, hardly any in the universe as a whole. But for the first few minutes in the Big Bang, the first 3 minutes, it was so hot that all the protons and the neutrons that were created start colliding with one another, and they start undergoing nuclear reactions. And neutrons and protons can collide to make a heavy form of hydrogen, and that heavy form of hydrogen can collide with, interestingly, an even heavier form of hydrogen, or it can collide with a proton to make a form of helium, and this hydrogen and that proton can combine to make another form of helium. In the first 3 minutes of the Big Bang, the universe was hot enough that these protons and neutrons could collide with one another and start building up the elements on the periodic table of elements. And we get the formation of hydrogen atoms, which are easy because hydrogen atoms are just a single proton. But we get the formation of helium and lithium on the periodic table. But there's a problem in the first 3 minutes. The universe is rapidly expanding. It's expanding so fast, and it cools off so quickly that just 3 minutes after the Big Bang, the nuclear reactions shut down. It gets too cold for nuclear reactions. So the universe does not have a lot of time to make elements because it's only got 3 minutes of nuclear reactions to do that. On top of that, it turns out that just after lithium on the periodic table of elements, there's a bottleneck. The next element on up from lithium, the form of beryllium that would be made is unstable, so unstable that the universe can't make it. This is what the periodic table of elements looks like today. This is what the periodic table of elements looked like 3 minutes after the Big Bang. There were only 3 elements in the whole universe: hydrogen, helium, and lithium. And I only include lithium here. There was a tiny, tiny amount of lithium in the early universe, so I include it here because there was some lithium made. But 3 minutes after the Big Bang, the universe was 75% hydrogen and 25% helium. There was no gold, there was no carbon, no nitrogen, no oxygen. I like to point out to students that chemistry class was a lot easier back then because it was just hydrogen and helium. Helium's a noble gas, so it doesn't underform molecules. The problem was there could be no chemistry class because there's no carbon and oxygen to make the chemists. Steve's webpage that has the periodic table of elements was a lot easier to build back then, but there could be no Steve to build it because there was no carbon or nitrogen or oxygen to make Steve. So that was the Big Bang in the first 3 minutes. So where did the gold come from? Because the gold didn't come from the Big Bang. The carbon and the oxygen in your body did not come from the Big Bang. So where did they come from? Well, we have to trace this hydrogen and helium gas over time and see what happens to it. So the next step after the Big Bang is that the universe continues to expand, and at first this gas is very evenly distributed, very smoothly distributed throughout the universe. But gravity starts clumping it together. And as gravity starts clumping this gas together, we can see clumps forming in the early universe. This is a picture of the glow left over from the Big Bang. This is a whole sky image. It's like one of those odd Earth maps where they try and show you the whole Earth map, so they disassemble the Earth and they spread the whole thing out. So this is a map that shows you the whole glow of the Big Bang of the whole sky. The light that you're seeing, it was taken by the Wilkinson Microwave Anisotropy Probe, that NASA satellite I mentioned a minute ago, and this is the glow. It was released 380,000 years after the Big Bang. But you notice that just 380,000 years after the Big Bang, matter is already clumping together. Gravity is already starting to pull it. And we can run simulations, starting with a very smooth universe, and just let gravity run in our simulations, and we can see how the universe starts gathering into clumps. And we go from the very smooth universe that we had early on to the very clumpy universe we have today. And any deep image of the universe, like the extreme deep view that was recently released by the Hubble Space Telescope, the deepest image that humanity has ever taken of the universe, shows us that the universe today is very, very clumpy. The gas isn't evenly distributed, it's clumped together, and the basic building block of the universe is the galaxy. This is a picture of what our Milky Way galaxy would look like if we could get outside the galaxy. But as I said before, we've never been outside our galaxy. Our children will not get outside the galaxy, and their great-great-grandchildren will not get outside the galaxy because it would take hundreds of thousands of years to travel out to this distance. It would not even travel out to the light. We would have been doing that right now. So this is another galaxy, NGC 1414, that we think looks like our Milky Way galaxy. If we could get outside the Milky Way and look back on it, this is what our galaxy would look like. Our galaxy consists of a few hundred million stars and giant clouds of gas and dust. Those giant clouds of gas and dust are where new stars are being born. Now, we don't see the Milky Way like this. We see the Milky Way like this because we live inside of it. It's like a giant pizza with a grapefruit at the middle. The grapefruit is this big bulge down here, and the pizza is a disc of material. But because we live inside the pizza, in the middle of the pizza, about halfway out from the center, when we look over towards the constellation of Sagittarius, we see the grapefruit down at the center, and then here's the list of pizza around us. Everything that you can see in the night sky, with one exception, is part of the Milky Way galaxy. These stars are in the Milky Way. We just happen to be the stars that are above us. These stars are in the Milky Way. Those are the stars that are below us. These are the stars that are in the Milky Way that happen to be all around us. And of course, if you think about a thin pizza, if you live in the middle of a pizza, there's not much pizza above you, not much pizza below you, but lots of pizza around you, which is why our galaxy looks like a line cutting through the sky. And the only thing that you can see with the naked eye is not part of our galaxy. There's a big fuzzy object in the constellation of Andromeda right here. And that big fuzzy object is a nebulous galaxy called the Andromeda Galaxy, about 2.4 million light years away from us. And I'm going to guess that here in the Hampton area, you're not going to see that because of all the light pollution, that you need to get out of the dark country skies in order to see the Andromeda Galaxy. Inside of galaxies, the basic building block of the universe are stars. And stars are the next part of our story. That's what happens to the elements. Stars are giant balls of hydrogen and helium gas. Our sun is a giant ball of hydrogen and helium gas. It's about 300,000 times the mass of the Earth. It's 109 times the diameter of the Earth, so the Earth would be a little tiny spot up here compared to the size of the sun. But the sun has no solid surface. It is a gas all the way to the center. And it is, as I said earlier, 74% hydrogen, 25% helium, and 1% everything else. Down at the center of the sun, because of the weight of all these layers of gas pushing down on the center, as they push down on the center, they compress that gas. That gas is really hot down there. It's at a temperature of about 15 million degrees. And there are nuclear reactions going on down there, and that is what powers our sun. And there are two basic nuclear reactions in the universe. There are fission reactions, where you take big elements like uranium and you break them into krypton, barium, and release a bunch of neutrons. Those are fission reactions. And there are fusion reactions, where you take light elements like hydrogen and collide them together to fuse or build bigger elements. Now, this one's important to us. Fission is important because this is how a lot of our electricity is generated. A fair bit of the electricity that's running the lights in this room in this projector are coming from nuclear power plants in Virginia. In Central Virginia, we have the Lake Anna nuclear power station. And at Lake Anna, they're taking uranium atoms, they're splitting them apart, and in the process, it's releasing energy, and that energy is getting turned into electricity. We also make nuclear weapons out of this. Uranium bombs and plutonium bombs are fission weapons. Fusion, on the other hand, where you take the light elements and combine them to build bigger elements, is something that we have not yet mastered, at least for generating electricity. We have, however, mastered this, if you can call it mastering it, in nuclear weapons, hydrogen bomb. We can do this reaction in an uncontrolled way, but we haven't yet figured out how to control it and harness it and turn it into electricity. But we understand fission and fusion nuclear reactions quite well, and you can guess which one powers the sun, because I've already said that the sun is 74% hydrogen, and so the sun is made mostly of hydrogen, and it's fusion reactions that power the sun. Deep down, inside the sun, in the core of the sun, but only in the core of the sun, not in the outer parts of the sun, just deep down in the core, it's hot enough, about 15 million degrees, where you can collide protons together and build up heavier elements. This is the set of nuclear reactions, the chain of reactions, that goes on deep down inside the center of the sun. What happens in the sun is a hydrogen atom, which is a single proton, which has a positive charge, and another hydrogen atom, a single proton with a positive charge, collide with one another. And they don't want to come together because
Indeed.
This shows what our sun looked like when it was born. This is the distance from the center of the sun out to the surface of the sun. This is the composition of the sun. So this is the core, this is the surface, and you can see that throughout the sun, when it was born at birth, the sun was mostly hydrogen and a little bit of helium. Today, the sun is 4.5 billion years old, so it's about halfway through its life. The sun has used about half of the hydrogen in its core and converted that to helium. Our sun is about halfway through its life. It is a middle-aged star. When the sun is about 10 billion years old, it will have converted almost all of its hydrogen into helium. And at this point, our sun will start to die, because there will be no longer any nuclear reactions going on down at the center. And our sun needs those nuclear reactions because gravity is trying to pull all that gas together. And the nuclear reactions are providing the force that balances against the force of gravity. Without those nuclear reactions, gravity will win, and the center of our sun will start to contract. And as the center of our sun contracts, it releases so much energy that it pumps up the outer layers of the sun into a red giant star. So we get to the red of our sun. The size of our sun today is the size of our sun when it's a red giant star. It would be enormous compared to the size today. And what's gotten talked about is the center of our sun is actually shrinking. The center is shrinking and getting smaller, and the outer layers are getting pumped out. And in fact, that center will eventually become unstable. And when it becomes unstable, it will blow off those outer layers. In its lifetime, our sun is converting hydrogen to helium. When it's a red giant star, at the end of its life, that core will get hot enough, and it can actually convert helium atoms into carbon, and some carbon into oxygen on the periodic table. It can only do that later on, because right now, it's not hot enough at the center of the sun to convert helium into carbon. The problem with helium is it has 2 protons. Another helium atom has 2 protons. That's plus 2 and plus 2. It's a lot harder to drive those together. Because it takes a temperature of about 10 million degrees to fuse hydrogen and helium. The temperature has to be over 100 million degrees to fuse helium into carbon, and our sun's not hot enough yet. But it will be in the giant phase, and it will fuse helium into carbon, and a little bit of carbon into oxygen. But our sun isn't big enough, and it won't do any more than that. And that's as far on the periodic table as our elements will go. Now keep in mind that the carbon, the nitrogen, and the oxygen in your body did not come from our sun, because our sun won't do this until it's dying. So it's not as if it did this long ago. This is what the sun's going to do at the end of its life. And this is what's going to end up. This is the ultimate fate of our sun. This white dot in the middle is a white dwarf star. It's the burned out core of a star like our sun. And this beautiful planetary nebula that you see around it, this glowing nebula, is the outer atmosphere of the star. The dead core becomes unstable, and it puffs off those outer layers and creates this beautiful planetary nebula right there. The problem with stars like our sun is all the carbon, the nitrogen, and the oxygen, it stays locked up in that white dwarf star. It doesn't return those elements back out into space to be used by future generations of stars. So the carbon, the nitrogen, and the oxygen in your body did not come from a star like our sun. The carbon, the nitrogen, and the oxygen in your body actually came from a much bigger star. Giant stars undergo different nuclear reactions. And so let's talk for a minute about the nuclear reactions that happen in big, giant, massive stars. And this is a really cool plot that shows you how much there is of each element in the universe. This tells you the amount of the element, and this is each of the elements listed here. And we know about this table, this is a logarithmic table, which means each one of these tick marks is a factor of 10. So just believe this. It looks like there's almost as much nitrogen as oxygen in the universe, but in fact there's something called a tick mark, which means there's 10 times as much oxygen as there is nitrogen in the universe. So these are the abundance of the elements. We know that hydrogen and helium are the most abundant elements by a lot in the universe. And then there's hardly any nuclear where they were born out, but here, if you look at that periodic table of elements, you'll notice something very interesting about the abundant elements. So can someone tell me what atomic number carbon is? 6. So what number is oxygen? What's the 10. That easy. 7. Do you see the pattern now again? It's the chemical elements. 6, 8, 10, 12, 14, 15, 18, 20, 22, 24, 26. The even number elements in the universe are 10 times more abundant than the odd number elements. Why is that? Why does the universe prefer the even number elements over the odd number elements? And another thing before we go on, to point out about this table, as I mentioned, the hydrogen and helium are most abundant. Look at what the third most abundant element in the universe is. It's oxygen. Save oxygen. You are made as the third most abundant element in the universe. After oxygen, you make mostly carbon. Carbon is the fourth most abundant element in the universe. You are made of the common stuff of the universe. Carbon and oxygen are not rare. After hydrogen and helium, they're the 2 most abundant things in the whole universe. Just go back to this question of the even numbered elements. What is it about the even numbered elements? It has to do with the way massive stars live out their lives. The massive stars can fuse hydrogen to helium. And when they're done fusing hydrogen to helium, they can fuse helium to carbon. And then they can fuse the undergo other nuclear reactions. They convert helium and carbon to make oxygen. Helium and oxygen can make neon. Carbon and carbon can make magnesium. Oxygen and oxygen can make silicon. And if you look at these reactions, you notice that the basic building block of all of them is the helium atom. 3 helium atoms make carbon. Helium and carbon make oxygen. So the basic building block of all the elements is the helium atom with number 2. If you start with a building block that's 2, and you put 2 of them together, you get 4, 6, 8, 10, 12, 14, 16. The way massive stars live out their lives is they fuse ever heavier elements, and they're always using helium. So silicon and helium makes sulfur, plus helium makes argon, plus helium makes calcium, on the periodic table until you reach iron on the periodic table. Massive stars in their lives will fuse hydrogen all the way up to iron on the periodic table. So this is the periodic table today. This is what massive stars do. During their lives, they fuse hydrogen, helium, carbon, carbon, oxygen, neon, to magnesium, silicon, sulfur, argon, all the way up to iron. The iron's really special. Turns out iron is the most stable element in the universe. There's no element that's more stable than iron. Because iron is so tightly held together that if you fuse these atoms of iron, this energy. massive, and the gravity is so strong that the atoms can't push back against the force of gravity anymore, and they give up, and the core collapses. And in about 2 seconds, the core of the star, about the same size as our planet, but weighs probably 2 or 3 times the mass of our sun. So it's many, many times the mass of the Earth, but about the size of the Earth, that core collapses. And when it collapses,